This unit will help us demonstrate the characteristics of angle encoders in the application. It can show us both the dynamic performance and the actual attainable accuracy. But first, a brief look at the design. 4 different absolute angle encoders are installed: a sealed optical RCN encoder, a modular optical ECA 4000 encoder, an inductive AMO encoder, and a magnetic ECM encoder. The axis is driven by a torque motor here. A Heidenhain control is installed here. And the dynamic characteristics can be viewed here. This trace depicts the motor current versus time for the different encoders. The motor current, specifically the noise of the motor current, is a criterion for the motor's attainable dynamic performance. Low noise gives us higher dynamic performance, and high noise gives us lower dynamic performance. Now let's run through the various encoders. This is the RCN encoder in the middle. I can select the speed and start the motor here. Now we see the current noise, which is this band here. This optical encoder's noise band is very narrow and uniform under varying speed. So high dynamic performance is attainable. But the trace looks much different when we switch to a magnetic encoder, which produces more noise due to its lower line count. This is the magnetic encoder installed at the bottom. Its noise band is much wider and fluctuates more under varying speed. This test can be performed for all the encoders. And this is how it looks when we compare the traces for all 4 encoders in a single graph. The 2 encoders with a very narrow noise band are the optical encoders, and the 2 with a relatively wide noise band are the non-optical encoders. So we can already see a difference between optical and non-optical, but we still want to consider the accuracy. To do this, we mounted a high-accuracy reference encoder on top and performed a comparative accuracy measurement in accordance with ISO 230-2, which is a standardized measuring procedure for determining the accuracy of rotary axes. It requires measuring 12 consecutively approached points per revolution, with 1 forwards and 1 backwards revolution. This entire process is repeated 5 times. The measured points are plotted, and a statistical analysis is performed, yielding the various parameters listed here. These include parameter M, the mean bidirectional positional deviation, and parameter A, the bidirectional accuracy of positioning. Both are displayed for each encoder. Here we see the RCN and ECA optical encoders, which demonstrate very high accuracy and repeatability. However, these non-optical encoders exhibit lower accuracy and repeatability due to their scanning principle and lower line count. So again, we see 2 classes, the highly accurate optical encoders and the less accurate inductive and magnetic encoders. To supplement ISO 230-2, we are also performing a further measurement of dynamic performance. This time we measured between the individual positions under continuous motion in order to show the dynamic accuracy characteristics. We measured at a very high sampling rate of 5 kHz and a speed of 20 revolutions per minute. This yields values similar to these orange curves, with 1 curve for forwards and 1 for backwards motion. We named the resulting parameter D, the dynamic positioning accuracy, which was evaluated similarly to ISO 230-2. Then we compared the encoders. Once again, the optical encoders exhibit no speed-dependent error. Here we should note that the scale is changed. Due to the lower signal quality of this magnetic encoder, noise is visible between the individual stopping positions. This inductive encoder, however, demonstrates accuracy fluctuations under varying speed. So the inductive scanning method exhibits speed-dependent accuracy behavior. This also explains the relatively wide discrepancy between positions during forwards and backwards motion. So that was a basic summary of the demonstration showing the differences between the various encoders.